morning. I hope everybody is ready to learn a little physical science this morning. As I go through, I may give you some instructions to get up and go do something, just to make you make sure that you're paying attention and following and understanding what's going on. We're beginning a chapter on light today. We had been talking about light just a little bit, in that it is a type of electromagnetic wave, and so it does follow all of the other things that we know about electromagnetic waves, and we're going to talk a little bit today about its behavior. And when I'm talking about light, I'm talking about the visible light spectrum. You can see light waves that have a wavelength between 450 and 750 billionths of a meter. Okay, you can see it. Now remember to pause as you go along so that you can write down everything that you need to write down in your notes. Make sure that you get all this, make sure that you understand it, make sure that you replay what you need to. But keep in mind, visible light is light that you can see. You don't necessarily need to know these numbers, but do understand that there is a range of electromagnetic wavelengths that are just the right size to go into your eye, so that your brain can process them and produce what you know as color. Okay? In order for you to see something, the light will go and bounce off that object and come back to your eye. And it's that light coming back into your eye that produces the image for you to see. If the waves are too big, they can't get into your eye. If they're too small, your brain isn't designed to process them. So they are special electromagnetic waves. As we know, they're produced by an oscillating or a moving electric charge. And your brain is designed so that you can understand what the different colors are in this visible light part of the spectrum. Okay. Now there are some types of materials that light can shine through a little bit easier than others. Opaque materials, however, do not let light pass through. You cannot see through opaque materials. They will absorb some light. Some of the light will be reflected or bounce back to your eye so it can have a color. However, no light will pass through. What I would like you to do right now is go and find something that you can put your hand behind and you can't see through it. Once you've found that thing, you put your hand behind it and you can't see your hand, that thing that you found is opaque. An example you can write in your notes is a brick wall. If you have a brick wall, you stick your hand behind it, you can't see your hand. Or if a person walks behind it, you can't see them anymore. So you would say that that thing is opaque. Okay? The next type of material we will talk about are translucent materials. Translucent. You can see through a little bit, but not really very clearly. Something that's translucent will absorb and reflect some light, but it's also going to let some of it go through. Okay, for example, some bathrooms have glass that is translucent. You can see through a little bit, but not very clearly. Wax paper, tracing paper. These are all things, if you put your hand behind it, you could see maybe the outline of your hand, but you can't see through it clearly. Or if you put it up in front of your face, or your friend put it up in front of their face, they could see through it a little bit, but not very clearly. So what I'd like you to do right now is I want you to pause this, get up, go find some wax paper in your kitchen. Put your hand behind it. Notice that you can see a shadow of your hand, but not your whole hand. Or go find something in your house that is translucent, something you can see through a little bit, but you can't really see through very clearly. And tomorrow when you come in, be prepared to just let me know what it is that you found in your house that you could see through but not very clearly. Tracing paper. Remember when you used to have a book and there would be paper that you put on top and then you trace the picture? You can see through a little bit but not super clearly. Those things are translucent. For those of you that like to cook, sometimes the directions will say cook your onions until they're translucent, which means that when you pick them up, you can see through them just a little bit. Okay, they're not transparent, they're not opaque. In other words, you can't see through them clearly and they don't block out everything. And translucent, you can see through a little bit, but just not very clearly. Here's this word I just mentioned, transparent. If something is transparent, you can see through it very clearly. Almost all the light waves will come through. It'll reflect and absorb some, but not very much. Window glass is a very, very good example of something that's transparent. Okay? If you look out through your window, you will see through it clearly, unless you have a dirty window. Okay. In which case, clean it and you'll be able to see through it very clearly. The image will be bright and crisp and you can see details through it. That's transparent. If you had maybe some colored sunglasses, you can see through them clearly, but maybe everything has a certain color to it. Those are also considered transparent, even though they have a colored filter, we call that, and it gives everything a little bit of a specific color tint, but it's still considered transparent because you can see through it clearly. All right, so why don't you go look out the window and see the pretty snow, and then you've looked through something transparent. Don't forget that when you need to stop this video and write things down, do it at your pace. Pause it, write it down, make sure everything gets in your notes. To review what reflection means, when something is reflected, it means it strikes something and bounces back off. Light waves are reflected all around us all the time. We couldn't see if it wasn't for reflection. Whatever it is that you're seeing is a result of the light reflecting off that object and coming back into your eye. Remember, we talked about the law of reflection before in regards to any type of wave, and that was that the angle of incidence equals the angle of reflection. You do need to know that for this particular chapter, this test as well. The angle of incidence equals the angle of reflection. And just to redraw the drawing that we already had, but it does need to go in this chapter as well. You have the incident beam coming in, the reflected beam coming out, and this little angle in here equals this little angle in here. So if this were a mirror, and you had someone here, and you had someone here, the person over here would be able to see the person that was standing exactly here. If the person were down here, the reflection wouldn't work the same way. The incident beam would be a little bit narrower, and so would the reflected beam. So the angle of incidence equals the angle of reflection. We have two types of reflections. We have a regular reflection and what's called a diffuse reflection. Regular reflection is what you're used to. In a regular reflection, it's like a mirror. It's nice and flat. The surface is smooth. You get a nice clear image when you look at it, or maybe a completely flat pond. that doesn't have any wind blowing at all. If you look in that, you're going to see a regular reflection. The image is clear, it's crisp, no exaggerations in it whatsoever. In a diffuse reflection, you have a bumpy surface. The image is poor. It might look garbled. You might have, if you're looking at a face, you may have the chin on top and the nose on the bottom and the eyes in the middle, because the surface is bumpy, and because the angle of incidence equals the angle of reflection, the images come out distorted. In a funhouse mirror, it's distorted, but in a way where it stretches out. Once again, there's more of a controlled bump in a funhouse mirror. It's not randomly bumpy, but it's still called a diffuse reflection. If you throw a stone into the water, it creates waves, water waves on there, but it creates a bumpy surface, so when the light waves come in and they bounce off, you're not having a nice, even reflection anymore. So, once again, in a regular reflection, the surface is flat. So all of the waves that come in bounce out in a nice, straight pattern. They bounce directly back, so the image is clear and crisp and not distorted. In a diffuse reflection, the surface is bumpy, so it'll come in and it'll bounce off using the angle of reflection. That normal might be down through here. So this part, if this is where the eye is in a face, the eye may show up a little bit lower when you see it and you're looking at the image that comes back to you. The nose might bounce out and go right to the top of the head, over the eyes. If you had a face here, this bounces in, this one bounces up. And then if this is where the mouth was when someone was looking in a bumpy mirror like this, the mouth would then stretch way down here, so you'd have a very funny looking image if you look into a bumpy mirror and get a diffuse reflection. So wherever they hit is going to determine where that normal line is and how the bounce is going to come when it bounces back off again. Remember refraction. Now a lot of this is review, which makes it very nice for your studying, because a couple months ago you had all this information before. So this should really stick this time. In refraction, the light wave gets bent because the speed changes when it goes from one medium to another. When we discussed it before, I talked about you have a light that goes into the water and the fish doesn't appear to your eye where it would be, because when the light wave bounces back off the fish, it bends a little bit and it makes the fish look like it's in a different place. The index of refraction is a number that represents how much of a bend that light wave has. It's a property of the material that shows how much the speed of light in the material is brought down. It's a number. Now when you come to school tomorrow, we will try to do a couple of things to illustrate this refraction property. It involves putting a penny in a cup and being able to not see it or see it based on this refraction property, because of the way the light bends when it comes into or out of that particular cup. A higher index of refraction means the wave is slower. So if you have a material that's more dense, you're going to have a higher index of refraction, a bigger number, which means the wave is going to slow down more. And when the wave slows down more, it bends more. Okay, so water has a lower index of refraction than a diamond. So water will bend the light less than a diamond. the light slows down more, it bends, it bounces around depending on the diamond cut, and when it comes out you get a little bit of a sparkle, a little bit of color, because those light waves have had an opportunity to bend around so well inside of that diamond. And it comes out to be quite beautiful if you have a skilled diamond cutter. And we had talked about that a little bit before in class as well. Another thing we're going to take a look at in class are prisms. Okay, prisms are basically those triangular pieces of glass, and when light passes through a prism, you end up getting a rainbow. Now, a triangular prism means that the top and the bottom of these prisms are triangles. Okay, the top and the bottom are triangles. Okay, and then the sides are rectangles. So we've got, oh, that's horrible. But we have basically a triangular shaped figure here. Let's try it with shape recognition and see if I can get a little bit better prism here. Slightly better broken prism. We have triangle on the top and bottom. They're made of glass, these triangular prisms, and we are going to get a chance to do some hands-on with them. They have a shape like this, similar to that anyway. And the light will pass through, it'll bend, and then it'll come out the other side and you'll have a rainbow. This happens in nature in a water droplet. Okay, the light waves come into the water droplet, and what will happen is it will bend, it'll reflect off the back, and then it'll bend again as it comes out. And then as it goes through this bending, the different wavelengths will bend more or less depending on which wavelength came in. White light has all the colors, but when it goes through a prism, either a triangular prism or a water droplet prism, it separates all those colors out, so you see a rainbow. The triangular prism will refract or bend the light twice. So the light will come in, it'll bend, it'll hit the two sides of the prism and come back out again. Or in the water droplet, it comes in, it bends, it bounces, and it bends. And then the rainbows will be created. A rainbow is made up of all the colors of light. Okay. There are 7 colors that the eye usually can see clearly. Alright, now there's other wavelengths in there, but the eye can come up with and see all the colors of a rainbow. From the longest to the shortest, we can use this name of this person that never actually existed, Roy G. Biv, and it helps us to remember the order that the colors go in a rainbow. Red, orange, Roy, red, orange, yellow, G, green, and Biv, blue, indigo, and violet. Okay, indigo is more like a purpley blue. So Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. And if you remember, the red is the longest of those wavelengths, and the violet is the shortest. So you're going from the longest wavelength to the shortest wavelength, and as I said a minute ago, the prism will split that light out. All those colors are present every time you see white. So as you're looking at this background here that appears white to you, all of those colors are present. And your eye interprets when it gets all those colors as white. When you look at this particular piece right here that looks red, it's just the red part that's bouncing back to your eye. Okay, that particular wavelength that sends a message to your brain of red. Okay, so the longest wavelength to the shortest wavelength. Roy G. Biv. And finally, your eyes can play tricks on you. You can see a mirage. Now, a mirage is not like they show it in the movies where you've got palm trees and those type of things. A mirage is simply a trick of the eye played where a distant object, something way off in the distance, kind of gets a rippling effect. You see that in the summertime sometimes when you look out on the road and it looks like the road is shimmering, because you see it looks like a wavy pattern. But it's created as the light waves are passing through the heated air that's coming up off of the pavement. And the heated air is a little bit different density because of its different temperature. Those air molecules are more spread out or less spread out because they're heated up. So when the light passes through, it bends the light waves a little bit. And so it makes it makes it almost look like there's water even out on a very dry road because of the way that that light is bending. It's called a mirage, and that is our technical science definition of that word that is usually very, very misused by Hollywood. But it's an image of a distant object created by light waves when they refract as they pass through these different densities of air. Okay, so what would be a good idea would be possibly to go and do a web search for images of opaque and translucent and transparent materials. That will be another way to get this information into your head. You might be able to go through and find some pictures, or at least remember what images look like if you throw a pebble into a pond. That could help you to understand and see the difference between regular reflections and diffuse reflections. If you have a prism, it wouldn't be a bad idea to take a look through it. We will be doing that tomorrow. So your job is to make sure your notes are in good order, look over them, read your book, and I will see you tomorrow. Have a blessed rest of your day.